Hello, class, and welcome again to our lecture in transmission lines and antenna systems. And we are in our second example. For this second example, we have a load of 75 ohms plus J50 ohms, and it is to be matched to a 50 ohm transmission line using a quarter wavelength matching section. So, this is a classic example of a matching using a quarter wave transformer. Okay, so we need to determine the proper location first, the proper location, and the characteristic impedance of the matching section. Okay, so as we already know, for every problem using our Smith chart, we must first normalize the value of our load impedance. And for this one, since we have 50 ohms as our transmission line impedance, then we know that to normalize this one, we just divide it with 50, and we'll have let me just write it automatically. We have 75 divided by 50, that's 1.5 plus 1J. So this is now the normalized load impedance. So let's go ahead and graph this one using our Smith chart. Smith chart there. So we have, again, what was that? 1.5 and 1J. So 1.5 is between 1.4 and 1.6. Okay, and we'll have to find 1J. 1J is right there. Here, this is 1J. And 1.5 is right here. No, right here. So let me draw that. 1 and 1.5. 1.5 here. So draw a circle, small circle, to specify that point. Okay, now we have created now our we have plotted now the point for our ZL. So the next step is to draw the VSWR circle, which we have already known from our previous example. So let's go ahead and do that. Specify the center point and then draw. Okay, that is now our VSWR circle. So I'm going ahead and turning off the fill. So that's our VSWR circle. Let me just go ahead also and turn off the fill of this one. There, better. Okay, so we have seen now that that is our VSWR circle. Now, since this is our ZL, I am sorry about that. This is wrong. Okay, we have both positive values. I'm sorry about that. This right here below are negative values of our reactance. So be careful about that. So let me just draw it again. We have 1.5 and 1J. So 1J is right there. So let me draw again. 1.5 and 1J is right here. And let me draw the circle again. Sorry. Okay, a bit off. There. Turning off the fill. Okay, so that's the correct point right there above, because we are all positive. Okay, anyway, proceeding with that one. From ZL, we need to move towards the generator until a point is reached where the line is purely resistive. Now, in order to identify which points of this particular circle here is resistive, if we move around this circle, we just have to find values or points where it would intersect with this line. Okay, so same case as we have been identifying our SWR. So in this case, we have 2 points actually on the circle that would intersect with this line. We have this point right here, and we have this point right here. So we could do, or we could use either of the following, or either of the intersections. But for this particular example, we are choosing the nearer one. Okay, so again, we are moving from the load towards the generator. Okay, because again, we are starting from the graphing of the load, so it makes sense if we move towards the generator. So this is the purpose of identifying this intersections class is to identify points where our line is purely resistive, and that is where we want to connect our quarter wave transformer. Okay, we need a point wherein our transmission line is purely resistive. So this again is the point that we are concerned with, and we need to measure, of course, the distance from the location of our load towards the generator and towards our point of intersection, because we want to know where along our line is the point wherein our impedance is purely resistive. So let me just go ahead and draw a line extending from the center towards the edge of this Smith chart, because I want to find out where am I located in terms of wavelength. Okay, so let's go ahead and draw that one from the center, passing through that intersection point and towards the edge of the Smith chart. Okay, so we have identified this one right here, and if we are looking at the towards the generator scale, we could identify that we are around 0.192, I think, right? So since we are now at 0.192, and we need to find out, okay, so we need to find out the location. That's the location, and we need to find the distance towards a point wherein our impedance is resistive. So we just have to measure this point towards that 0.25 in order for us to identify the distance, and that would give us let's just do that right there. So we know that ZL is at around 0.192 wavelengths, and the nearest, okay, point wherein we could say that this is resistive is around 0.25. So in order to know the difference, let's just notate as the difference of wavelengths. Let's just do that numbers, 0.25 minus 0.192, and that should give us a value of 0.25 minus 0.192. So we have 0.058. Okay, so we have 0.058 wavelengths from the load if we are trying to draw this one. So we would need at least to move from the load around 0.58 058 wavelengths, and that would be the location now of where we would insert our quarter wave transformer. Of course, the length of this quarter wave transformer should be 1/2 wavelength, right? I mean 1/4 wavelength, quarter wave transformer. So this is now the quarter wave transformer. So we are placing it 0.58 wavelengths from our load. So the next thing to solve here is the value of the characteristic impedance that we need to use in order for in order to balance this circuit for our ZL and our transmission line. And in order to do that, let's go ahead and remember also that our characteristic impedance for the line is 50, right? And around right here, okay, let's just try to read the value of our SWR, or the voltage standing wave ratio. And we know that the voltage standing wave ratio right here is 2.4, and this is also the value of the real of the impedance of our point at this point, and that is purely resistive, right? So that the value of this point is 2.4, this intersection point is 2.4, and that would also be the value of the impedance of this line at that point. And if we multiply that 2.4, okay, So let's go ahead and uh, let's say impedance at purely resistive point is equal to 2.2. That is normalized, right? So if we want to have the non-normalized value, so we should multiply that by 50. So we'll have around 100. 2.2 times 50 is around 110. Is that 2.2? Wait. Oh, that's supposed to be 2.4. Okay, so 2.4 times 50 is 120. Okay, so we'll have 120 ohms at that particular point where we would insert our quarter wave transformer. And in order to solve for the impedance of the quarter wave transformer, then we just need to make use of this value. Okay, so the formula is the characteristic impedance of the quarter wave transformer is equal to ZO times RL, which is in this case we are using the 120 ohms because seeing from that point we look at this point to be having a ZL of 120 ohms because right we are looking towards the ZL plus the 0.058 combination. So that would give us a 120 ohms in terms of the combination. This is actually similar to solving the input impedance earlier on. But right now, we are just solving it at the point wherein we have purely resistive components. So in that case, ZO in this case is equal to 50 because that's the characteristics impedance of our line. We should multiply that one with 120, which is the value of the resistance at the point where we find it resistive. Okay, so that's equal to 120. So that would give us approximately a value of 77.5 of ohms, and this should be the value of the characteristics impedance of this quarter wave line that we would insert in our circuit. Now if we try to draw this one, so we'll have, this is the original line which has a ZO of 50. This is the inserted quarter wave transformer with should be an impedance of 77.5, and of course extending again the same ZO is equal to 50. Okay, because we have inserted this between, then extending to 0.058 wavelengths, then we connect our ZL. So that is now our circuit. So let me just go ahead and color it green for our quarter wave transformer. Okay, so that's our second example for this Smith chart and matching our load impedances.